All right, everyone. Let's get started with our seminar. It's a new time, 12 p.m. today, so thanks for you all for being here. And today I'm very pleased to introduce our seminar speaker, Phil Bresnahan. Phil received his PhD and master's degree in oceanography from Scripps Institution of Oceanography, and before that, he got a bachelor's degree in chemical engineering from Lehigh University in Pennsylvania. He's now an assistant professor at the University of North Carolina, Wilmington since 2020, where he leads the Coastal Ocean Applied Science and Technology Lab, also known as COAST. That was a clever acronym on this one, Phil, so well done. And I guess the motto of his lab, which I think is really neat, is to develop and communicate solutions for our most pressing environmental questions and problems. So they do a lot of work with sensors of their own, or also like commercially available sensors for in situ monitoring. They do some satellite and they use satellites and drones for remote sensing, and they develop new techniques for time series analysis and also machine learning to better understand our changing ocean. And one neat aspect of Phil's work is that he's done a lot of work to facilitate public participation in scientific research, and he's most well known for his role in the development of a smart fin project, which I think I'll talk about today, which is a surfboard fin that's equipped with a temperature sensor and a motion tracker that has been distributed to, I think they've built about 300 fins so far, and they've been used all over the world. So that's a really neat citizen science project that is helped developed. Phil has 19 publications so far, which is very impressive for someone of his at this stage of his career. Most of it deals with in situ sensors and ocean acidification research and also carbonate chemistry, but there are some new ones up there that I haven't looked in details quite yet. So before we get started, I need to remind you of the rules of the road. So I'm going to read through those, so please bear with me. For the online participants, remember that you will be muted throughout the seminar. Do not attempt to turn on your video or share your screen during the talk. And just like in a normal seminar, there will be an opportunity to ask questions at the end of Phil's talk. So once the speaker is done, you can use the Zoom raise your hand feature to notify the meeting host, aka me, that you like to ask a question. And then so that feature is located under the reactions tab at the bottom of the Zoom window. By now you should all be quite familiar with this, I think. And of course, you'll be invited to turn on your video during the questions at the end of the talk. And without further ado, please, I'll leave the floor to Phil. So thank you, Phil, for being here today.
Well, thanks very much, Max, and thank you all for being here. Thanks for accommodating my East Coast schedule and moving your seminar a little bit earlier for me. As Max mentioned there, I will be talking a bit about SmartFin, but I'm not going to be showing this video that's on the back right now, which is some actual live data coming in from SmartFin's wall, overlaid on top of some surfing footage. So just a little eye candy to start us off here, but I'll talk more about the science and technology behind that. So thanks again for the introduction and invitation. What I wanted to talk about today is going through a couple different topics and sort of layering it on as we go. So starting off with carbon in the ocean, which, as Max mentioned, is one of my main focuses. And then talking a bit about where the Internet of Things is fitting in with oceanography and ocean sensing right now. Then bounce back to carbon sensors in the ocean, Internet of Things sensors in the ocean, and then kind of shove it all together with carbon IoT sensors in the ocean. So first, where I fit into all of this, I have a hard time trying to figure out exactly where I fit into the puzzle because I'm trained as both a scientist and an engineer. And so I thought I would try to lay this out partly for my own sake, and hopefully this is helpful in understanding where I fit into this puzzle. So the science, the sort of vertical, if you will, of where I fit in, what I'm trying to work on, is on the study of coastal change. And I'm especially interested in water quality parameters like ocean acidification, deoxygenation, eutrophication, and other generic water quality things, as well as more recently in this blue carbon space, especially in where human impacts come into the picture for all of these. And then my horizontal, if you will, the kind of cross-cutting theme for how I approach all of these things is these tools and techniques of engineering sensor development. I've been especially interested in the low-cost space recently, as well as participatory science, which some folks call citizen science or community science, depending on kind of the intended outcomes of that work. And so I'm going to try to talk about this intersection today, my work toward developing technologies for coastal water quality change detection. To set the stage for my exact field of research, I wanted to step back a few years, almost a decade now, to this review, which is titled "A Time Series View of Changing Surface Ocean Chemistry Due to Ocean Uptake of Anthropogenic CO2 and Ocean Acidification." And if you're not familiar with this paper, what Nick Bates and others looked at was the long-term time series stations where they collected dissolved inorganic carbon and pH and other inorganic carbon parameters and other nutrients as well on top of that, and biologic components. And they were able to start to really look at what we already knew was happening, but hadn't really pieced together in this global sense previously. The graph on the right-hand side shows data from all of those stations ranging really across the world. And we're looking at pH over the last now 4-ish decades or so. And the numbers that I really want to call to attention are those that are in the upper right-hand corner of each of those graphs here. So we're looking at an annual, this is the slope, by the way, we're looking at the annual rate of change across all of these stations for pH. And so this is the number, I'll come back to refer to this number quite a bit throughout the talk. So we're looking at an annual rate of change of about 0.002. That is what we refer to as ocean acidification. And that is, it's really interesting to see here that it's a really globally consistent thing. Of course, there's a little bit of variability in that 4th decimal place, but more or less a consistent picture in surface ocean pH changes. Most recently, I've been working toward the coastal ocean, and this picture tells us the first part of that story. So I think everyone in the audience is probably well familiar with what is going on in this pie chart here, just representing the surface area of open oceans, shelves, estuaries, and so on. And of course, we know that the dominant water feature on the surface of our planet is open oceans. But when you look at it in terms not of surface area, but rather carbon dioxide flux, now on the left-hand side, we have our open oceans. And indeed, this is the largest bar here. So this is definitely our largest total carbon dioxide flux. But it's interesting to me, at least, that the other bars here are almost the same order of magnitude or pretty close, just a factor of maybe 5 or so less. And all the way out in lakes and rivers here, we're looking at the opposite direction, but a very similar magnitude. And if you were to sort of divide, if you could mentally divide this pie chart, this bar chart by the pie chart and get a flux per unit surface area, the story would look really different. So open oceans, the flux per meter squared is pretty small, whereas estuaries, wetlands, lakes, and rivers, the flux is large, and the error bars are extremely large. And so where I am trying to focus a lot of my effort right now is shrinking these error bars. And I'm going to talk over the next couple slides about how I am trying to do that. And of course, it should more or less go without saying that beyond carbon cycling, there are all these other reasons to study coastal ecosystems, and a lot of reasons why it's fun to do so also. Their population centers serve for a lot of employment, recreation, storm protection, water purification, and the list goes on there. So switching briefly to this topic, the Internet of Things, this is one of the buzzwords of maybe the last decade, 15 years or so, but it hasn't really permeated all fields of science and engineering and society at large. So I wanted to kind of step back and talk about what this is in case anyone's not familiar with it. The overall idea is that the IoT is anything that's connected to the cloud. So some device that's sending data back to the internet in some fashion. And in a lot of cases, these things don't necessarily need to be. You can see some kind of ridiculous examples here, a vacuum and lights and ovens and things like that. And so there are a lot of things that we're connecting now just because we can. As a quick aside, one of my favorite Twitter accounts is the Internet of, I'll let you fill in the blank here, which is a collection of all of the worst aspects of the Internet of Things. So please do not turn off or unplug your oven while it is updating. Trying to update the firmware on my shoes right now. So again, the point here being that we are connecting anything and everything to the cloud right now just because we have the technology. And while I show this as a ridiculous example of how we're doing that, this movement has had some real benefits in science and technology development because it has made these components less expensive. It has really magnified the amount of available literature out there in terms of getting started guides and community forums and folks that are eager to help each other out to add some sort of IoT capability to their technology. And I want to take this other step back to also acknowledge that we've been doing IoT in oceanography for a really long time, even though we haven't necessarily been using that terminology. So I don't want to by any means suggest that I am at the forefront of IoT in oceanography. The Argo program, all of these other sensor networks, we have had connections to satellites and cell modems, more recently Bluetooth, Wi-Fi, Ethernet, certainly. All of these other things that are getting our data back in real time for a pretty long time, and just now starting to use some of these other buzzy terms as well. So a lot of my work, as I mentioned, is focused on carbon sensors in the ocean, and both from the development side as well as applications. And I got my start in this field working with this sensor called the Honeywell DuraFet, which is a sensor that is extremely stable and robust and has been shown over a ton of different studies now to work exceedingly well across a wide range of oceanic conditions, including all sorts of different ecosystems all over the globe. These have been deployed hundreds, maybe even thousands of times at this point, and most recently have even been incorporated into the International Biogeochemical Argo program and are profiling to 2,000 meters depth. What is really great about the sensor is that they're extremely stable and they're extremely precise, but they relate pH to a voltage through the Nernst equation, which if you haven't taken Chemistry 101 in a while, I'm not actually going to bother to show the equation other than to say that the Nernst equation has a constant in it, which is an offset which has to be determined through a manual calibration. There's no theory that will allow us to get to this constant. And so therefore, the accuracy for these devices is only as good as the calibration. And maybe that goes without saying for a lot of devices. We should always assume that there's a certain amount of calibration or at least validation required for our technology. But it's especially the case here. If you put an offset of 5 in, your pH will be off by 5 units. If you put an offset of 0.01, then you can really dial things in a little bit further. And what we learned through some of the early studies with these devices is that with a pretty good amount of technical care and attention, we could get down to about plus or minus 0.024 uncertainty. And remember, we're talking about this versus our rate of ocean acidification, which is an order of magnitude smaller than that. So in order to actually try to unravel what's happening in the global ocean over these decadal scales, we need something that's a lot more accurate than that. A semi-independent study looking at a whole bunch of DuraFets deployed across mostly Southern California found a really similar story. What we're looking at here is 6 different subsets of, or subplots of metacresal purple, which is considered the gold standard for measuring pH in the laboratory, versus the ISFET or DuraFet pH on the y-axis here. And you can see there's scatter about that 1-to-1 line, and a perfect sensor to discrete sample matchup would of course have all of the points falling right on that line, which is not at all what we see here. And to add in some statistics here, plus or minus 2 times the standard deviation for all of these sites is right around 0.1, 0.2 or so. And the reason for this is not just that people aren't taking care to calibrate their sensors, it's also there's natural variability. If you don't time your discrete sample exactly with the moment that your sensor is sampling, then you might be a little bit off. If you have to leave your sensor in a remote location for an extended period of time, you're not able to get back to it, then it would be even more challenging to collect these discrete samples and refine that calibration even further. A group of people put together this report, this governance plan a few years ago, led by Jan Newton, Dick Feely, and others. And they wanted to say how we could define these different thresholds in pH, not thresholds in terms of when do ecosystems really start to feel the effects, but what can we call a pH uncertainty that's acceptable for understanding relative patterns and short-term variation versus climate scale changes, these 0.002 scale changes. And so they defined a weather, what they call a weather scale uncertainty, and they define what they call this climate scale uncertainty, so 0.02 and 0.003 here. And with these metrics in mind, we set forth to see what other ways we could come up with to really improve the accuracy of the DuraFet and this whole class of sensors. One of the approaches that we've been working on recently, this is a collaboration that I was working on when I was back at Scripps Oceanography, also with Yui Takashita up at Mbari, and my former group back at Scripps with Todd Marks, Taylor Worth led the engineering for all of this. The goal was to add this external reagent, a tris in artificial seawater reagent, to the standard CFOX, the combination of that DuraFet with a bunch of other instruments, and see if we could use this reagent to periodically autonomously calibrate the CFOX sensor. And so that's what you see here. The black housing on the right-hand side of this middle figure here, as well as all of the white parts that are connected to it on the right-hand side, that's a standard CFOX. And then in this PVC housing on the left-hand side, I realize the laser pointer is pretty glitchy here, so I apologize for that kind of lagginess there. But the PVC housing on the left-hand side is storing our tris buffer reagent. And by periodically pumping, instead of ambient seawater through our system, and instead using the tris buffer, we're able to get this autonomous calibration. Tris, I should mention, is extremely well characterized across a range of oceanic temperatures and pressures. And so as long as we have pretty good physical measurements, we know exactly what the pH of that tris is at any given time. And therefore, we're able to get a really good calibration on this instrument. And I'm showing some data in the background here. I don't want to get too deep into the data themselves, other than to show a group of collaborators that Yui led out in Australia collected over 100 discrete samples, which would be this just remarkably large effort to try to refine the calibration on a particular sensor. Huge amount of work going into collecting those discrete samples and actually running them back in the laboratory. And then we compared that to what the in situ, the self-calibrating CFOX in situ autonomous calibration did. And I'm throwing back up the McLaughlin et al. Numbers here so that you can see this is, again, the semi-independent analysis of how how these different sensors perform when other folks deploy it using kind of best practices, our best ability to collect these discrete samples. And then overlaying on top of that, I'm showing what we were able to achieve with our TRIS-based calibration. With the internal reference electrode, we were able to get down to a standard deviation of 0.005 with 15 standards. And the external reference electrode, and I'm not going to get into the distinction between those two electrodes, but both of these are built into the standard CFOX. We were able to get all the way down to 0.002, and again with 15 samples. So really starting to approach those climate scale uncertainties that I mentioned. In the far right-hand column here, you see this other parameter. This is basically back calculating our 95% confidence interval. So if we were to input this standard deviation, how many samples would be required using the TRIS-based calibration to actually get what we would consider to be this climate scale uncertainty with 95% confidence. And we found that using the TRIS autonomous calibration and the external reference electrode, only 2 samples would be required to do that, versus in the field, it would take about 35 discrete samples to do the same thing. So really, really marked improvement here. Obviously, this is a large and somewhat clunkier system, and it would be really nice to continue to shrink this. We are continuing to put effort in to see if we can shrink the volume requirements for this so that we can use less and less reagent and facilitate deployments. But really nice improvement here in our overall accuracy. And to bring it back to why we would actually want to do this, of course, we talked about those standardized thresholds, weather versus climate, but then we also want to think about direct intercomparison of various sensors and methodologies. So if we were using multiple different CFOXes and doing a hot swap of one to the next every time we go out to service an instrument, we need to know that those two are actually reporting the same number because the conditions are the same, and not because there's some offset during a time of change. And of course, there are also different methodologies. So how do we compare these sensor values to discrete samples? How do we compare these ISVET-based sensors to other spectrophotometric sensors and new microfluidic technologies and things like that? So this has been really helpful for that. And then, as I mentioned, trying to get to remote locations can be nearly impossible for long periods of time when these might be deployed. So that can really help. Ultimately, all trying to work toward understanding organismal and ecosystem thresholds more exactly. How can we really try to prescribe thresholds on any of these things if we don't even know the pH with all that much certainty? One of the next things that I tried to do with a lot of this, and Max talked about this in his very nice introduction, is see if there are ways that we can get some of the science that we're doing in the lab and in the field to connect with local communities a little bit more. And so this is a picture from grad school that my good friend and colleague Yui Takashita, who I'm assuming many of you in the audience know from just down the road from you there. Yui took this picture of us trying to strap a sea fox onto the bottom of the stand-up paddleboard, which we thought at the time was a good idea, ended up being a complete disaster. There was so much drag from this device. It was so heavy. You can see the foam pads that are ratchet strapped there. It really didn't work. There was too much drag. The first paddle stroke I took, I pulled myself right off the front of the paddleboard. The paddleboard didn't move at all. But what this did was it allowed us to start talking to the community a little bit more about the variability that we were studying in the nearby kelp forest and seagrass beds. It also allowed us to help recruit a mechanical engineering student from upper campus at UC San Diego, Taylor Worth, who was at the time an RU student, now a PhD student at Scripps, and doing some excellent work with the Argo program, the self-calibrating CFOX, and other projects. Taylor took the design on the previous slide, everything that you see here, and shrunk it down to fit into this really nice hydrodynamic housing that you can see on the bottom of the stand-up paddleboard there. I liken this to sort of a remora. It's just Velcroed onto the bottom of the paddleboard. And it allowed us to go out and map the pH and oxygen variability in the shallow water ecosystems, in coastal ecosystems, where it might be really challenging to get using other methodologies. One of the most exciting studies that we did with this was, I'll start from the right here. So on the right-hand side, you can see the aftermath of this study. We did a 24-hour study that was led by Professor Andreas Anderson and others at Scripps. And we took a group of middle and high school students out, and we sampled every hour on the hour. And you can see, as I said, the aftermath here, everyone really conking out at the end of the day. We did take shifts, of course, so people had breaks in the middle of the night there. But a really exhaustive study of the Mission Bay, upper corner of Mission Bay. You can see here, this is a marine protected area, or a reserve rather. And we were able to paddle out there with the paddleboard as well as a kayak and collect a bunch of discrete samples alongside this autonomous sensor that we described, that we call the WaveFox. And what you're seeing here as this illustration clicks through is every hour's worth of data. And the color represents the different variability in pH. You can see the deep reds are about 8 pH, and then the blues get all the way up to 8.4. So almost a 0.4 swing in pH. And as you can see here, everything that ticks through, this one, for instance, is showing the deep blues all the way up in the top left extent of that area, where there are shallow seagrass beds, and we were actually able to observe this photosynthesis respiration cycle in a way that we hadn't managed previously using discrete samples. We also did collect a ton of discrete samples. We went out to 8 different points along this transect and did collect some discrete samples, but we didn't have nearly the same spatial resolution that we got from the WaveFox. We weren't able to get quite up as far into the outer reaches of those seagrass beds. And so this proved to be a really nice way to access some other areas. You can see a really nice illustration of that kind of in the middle, bottom middle here, where the WaveFox on the bottom of the paddleboard is in a seagrass bed that's maybe only about 1/4 of a meter deep. And so you really wouldn't want to take anything with a propeller out here. You would even struggle on some kayaks to get into areas like this. And again, without an autonomous sensor like this WaveFox, it would be really challenging to collect such a rich data set. So we're really excited about this. Now, coming back to one of our other topics, before I kind of connect all of this, I want to talk a bit more about some Internet of Things sensors in the ocean and connect this with what Max described as the SmartFin sensor. So here's an illustration of the smart fin sensor, nice silhouette of it at sunset. And you can see that it really pulls out some of the electrical components on the inside. What you're looking at here, it's a combination of temperature, GPS, motion, and then a wet dry sensor. Some of them have solar charging. They all fit in standard fin boxes and meet performance specs. So we have geolocated temperature sensors. We're working on algorithms to extract some wave information from that motion data using the inertial measurements. The bottom four here are all really nice for the user experience. The sensor turns itself on and off and knows if it's in the water or not. All the user has to do is keep it charged and then go in the water. The solar charging part obviously adds some nice power capabilities. It doesn't charge a whole lot under the water, but it can while it's sitting on the beach. And then the very bottom two bullets are extremely nice because we can give these devices to surfers and it will fit directly into their board. They don't have to strap some additional sensor on. They don't have to worry that their surfing is going to be impaired in some way by the performance of the fin. We are trying to make this as community friendly as we possibly can. We also have cellular data transfer on there. So this little figure on the right-hand side here, the encoded cellular transmissions, that's just our gobbledygook of the encoded data that we're sending over the cloud. And the advantage here is that we get data back as soon as the surfer steps basically onto the beach. As soon as they flip their board over at the end of the session and it's able to connect to the closest cell tower, the data starts streaming back. And then we have a free and open data portal that we're working with IU's partner, Axiom Data Science. They manage a lot of, if you're familiar with Senkoos there, or Skoos or Nanakoos, all of these other ocean observing systems. We are working with the same group that does all of those portals, or many of the IU's portals, which has been really nice because it means that one, we have access to all of the quality assurance and the Quartile quality assurance for real-time oceanographic data. We are putting our portal in a place where people might otherwise be going to look for whatever it is that they're after. And they don't necessarily have to just go to smartfin.org or whatever to find the data. Some of the exciting advances here, I want to talk first about the amount of student engagement. I've really, to be honest, I have to admit, I've lost count of all of the folks that have volunteered time to contribute to this project just because they're excited about it. They want to get that hands-on learning experience. Of course, a lot of folks want to get in the water and actually surf with the thing. But there are 12 undergraduate students and 4 graduate students that have really contributed above and beyond in the development from left-hand side of this figure to the right-hand side to get the smart fin to its current state. So of course, what you see on the left-hand side here wouldn't be anywhere close to something that could fit into a surfboard fin. But as we continue to refine things and shrink them down more and more, we got to the right-hand side, which is very close to our current edition of the smart fin, which has all those sensors I mentioned. We have our full custom engineering stack, which means we have our own custom hardware, our own firmware running the thing, data analysis software, and cloud visualization software. We're also working on some water quality sensors, and I'll come back to that in a couple slides, so gloss over it for now. I don't think those are going to be available in the very near future, but I do think that in a couple of years, we will be able to integrate a couple of those. And then the other exciting thing from a distribution standpoint is that we have data coming back from 5 different continents. We've distributed 300 of these and collected close to 3,000 hours of data. So 2,800 sessions, where a session is any amount of time that a surfer is in the water. So about 3,000 hours worth of data. And then we licensed this technology to a nonprofit for manufacturing a couple of years ago. They, as with just about every other electronics provider, have had all sorts of trouble with supply chain issues and have had a really hard time actually getting the fins built, which is really tough to see. We're really excited about this project, but we're currently left with an inventory of about 3, which we're using for R&D. Even though we've distributed 300, we just don't have the electronics available. The integrated circuits we don't have available. So hopefully that supply chain issue will be alleviated in the near term, and we'll be able to start producing these again. And we're really excited about all of the engineering capabilities, but then more so the scientific connections. And then of course, the community building and community outreach side as well. When thinking about what we can actually do with the data, one of the really exciting areas that we've worked in so far has been in satellite remote sensing validation, as well as comparison with other in situ sensors. We found that the density of observations from the SmartFin could really help validate some remote sensing imagery, some thermal imagery from Landsat and Sentinel satellites, and saw some really nice improvements in the actual algorithms going into taking the radiances that those satellites receive and converting it to temperature by comparing it with the SmartFin. The SmartFin, by the way, is calibrated to a NIST standardized temperature sensor, and it's accurate to plus or minus 0.05. So we have a very accurate thermometer in the water and are working on some other improvements to speed up response time and try to get even faster response measurements here. One of the other sets of questions that we're starting to look into and collaborators have been looking into with this device is how variable some of these coastal parameters are in areas where we might not otherwise have easy access to observational technology. So it's a pain to deploy buoys in the surf zone. It's a pain to leave them out there unattended, but surfers are actually there all the time, of course. And so by working with this community, we can really expand the richness of our data sets. We do, of course, recognize there are biases with this. Surfers aren't often out in the middle of the night and when it's flat and when it's extremely windy or things like that. So we recognize there are limitations, but we do think this can fill in some important and meaningful gaps. A lot of common surf breaks happen to be right over coral reefs, as well as rock reefs with seagrass beds near kelp forests and mangroves. We could put these on stand-up paddleboards as well and do larger transects, longer transects, and mapping exercises. And so there are a lot of really natural tie-ins with the surf community and other paddling communities. We're also interested in just watching from the geolocation data, where are people surfing on a year-to-year basis, and how is that changing as sea level rise starts to swamp some breaks, maybe open up some other breaks, and maybe some beaches are able to continue regenerating the sediment supply that's needed so that, or the beaches are already large enough so that the slope isn't changing significantly and those waves are still high quality. Coastal development being another really big one. We've been working a bit with the Surfrider Foundation, which got their start in trying to work with coastal developers and make sure that surf breaks were protected. And then where I get really excited as a sensor developer is the things that we haven't even thought to ask yet. So we know there are all of these other areas where we just haven't had the data yet to even know what question to ask. And I'm quite excited to start to contribute to filling in some of those gaps so that we can. Community engagement has been a really huge part of this project as well. This has been one of the most exciting parts of the project. We've gotten a lot of press for it. In fact, more press than we might deserve based off of the distribution and science so far, but it goes to show the combination of science and surf community and really trying to engage the community as much as possible. I always like to show these two screenshots here, the publication of some scientific data in Surfer magazine, as well as this press that we got for surfing in Science magazine. Just a really nice combination for folks who are familiar with the surf industry at all. You might recognize Kelly Slater up here in the upper right-hand corner, considered the greatest of all time in men's surfing, holding a SmartFin. So it's really, this project has really opened up access to a lot of different communities, a lot of different groups, and given us the opportunity to really get out there and talk about what we already know is happening in the ocean to communities that might not otherwise have access to that information or be regularly reading about it. And it's also been, of course, providing us this opportunity to collect new data. So we've been all over the place. There's some photos here from Australia. We've given talks at all sorts of different bars and pubs and high schools and literally on the beach multiple times. And so again, it's just been this really nice opportunity to get out there and talk about the things we love, as well as the changes that many of us are concerned about and want to do more about. Then trying to shove a couple of these topics back together to really bring us home here, I took a lot of the work that we did with SmartFin and started integrating that with some of the work that we were doing on our pH sensors. To set the stage for that, starting in the upper right-hand corner here, just north of Scripps Oceanography in San Diego, we have the Carlsbad Aqua Farm, and they're raising multiple different species of shellfish there in that aqua farm. And they have, as many groups, especially on the west coast of the US, been really interested in changes in pH, changes in the omega saturation state, and also looking at changes in all sorts of other things as well. But if you're a shellfish grower, if you're an aquaculturist, having that information after the sensor is recovered and after someone has taken the time to download and process the data is not necessarily going to be all that beneficial to you. You really need access to that real-time information. And so we integrated a lot of the electronics from the SmartFin and added this really inexpensive cell modem to a surface buoy here. This is a photo on the bottom right of the Carlsbad Aqua Farm, and only a couple $100 worth of buoy parts. The SmartFin electronics themselves are only a couple $100 as well. Frankly, the most expensive part on the whole thing for anyone who works in sensor deployment or development, the most expensive part was the Teledyne impulse cable that connected our unit from the surface down to the actual CFOX instrument that was making these measurements. But using these electronics, which we'd already developed for other projects, and a pretty quick integration, we started streaming data to a Google Sheet through the cellular modem. And now we have access to real-time or near real-time information on the pH. And we can actually work with the shellfish growers to send alerts when pH goes below in a level of concern, or to ourselves when we might want to go out and service the buoy and figure out, is it biofouling? Has something maybe dragged it a little bit further away from its intended mooring location, or something like that? One of the most exciting applications of this technology so far was from the beginning of the COVID pandemic. So we're looking, I just have the month and day here, but we're looking in early 2020. I don't by any means mean to suggest that COVID itself was exciting, but the sensor deployment was exciting because while so many of us were stuck at home and unable to really kind of continue with laboratory work or other parts of our scientific careers or lives as a whole, we were able to continue collecting data from the Carlsbad Aqua Farm. During that same exact time, there was a bioluminescent phytoplankton bloom of Lingulodinium polyhedra in Southern California. And we watched as this bloom started to wash its way into the Carlsbad Aqua Farm area. So I have this first part of the box of the graph highlighted here. By the way, I should mention we're looking at the pressure, salinity, temperature, and on the bottom two panels, we have pH and oxygen. All of these parameters being measured by the CFOX. And what I want to draw your attention to is we have a little bit of precipitation happening in early to mid-April, followed by this fairly sharp increase in temperature right around the beginning of May. And a lot of folks suspect, and I'm not a biological oceanographer, I'm not going to pretend to know everything that's going on out there, but a lot of folks suspect that it was this physical setup, this increase in temperature leading to an increase in stratification that allowed these Lingulodinium polyhedra to thrive, to bloom, which resulted in these really severe swings in pH and oxygen. So especially in oxygen, looking at the oxygen in micromolar, swinging from 0 at night all the way up to 200, 300, even 450 micromolar in the daytime during the peak hours of photosynthesis. And so seeing these really sharp swings, this was also, of course, tidally driven in this particular part of the estuary there. And the next really exciting, scientifically exciting part of this was that we watched as that bloom crashed, and as the decay of the bloom really was the dominant signal. We watched as pH really hit the ground. It went straight down to about 0 and flatlined at about 0 for a pretty long time, with some semi-diurnal peaks due to the tides and due to diel photosynthesis as well. But we saw this near flatlining of dissolved oxygen. And during this flatlining of dissolved oxygen, we watched pH continue to decline. So as we remove all of the oxygen from that system, the pH continues to decline. We continue to see this respiration signal or other forms of oxidation occurring in that ecosystem. And this combination of parameters was really nice to be able to describe a little bit more of what was happening out there. And so if you're interested in the science behind that, again, I supported largely the technology side, but if you're interested in the science, I'd refer you to this paper that my colleague Kenesha Shipley just published a couple months ago. One of the next big projects that I'm really interested in, also in the carbon IoT space, is Delta PCO2. So what you're looking at here on the left-hand side first is this Delta PCO2 sensor, where the very top and the very bottom are silicone coils that are, on the case of the bottom, submerged in water. The one on the top is in open air, and you can see that a little bit better on the right-hand side here. So the water line, these are set to deploy on floats, or in this case, a floating dock, so that the water line is right around the midpoint, the midline of that sensor, keeping, again, the bottom submerged in water and the top exposed to the air. And so we're able to get this delta PCO2, the air minus C differences in PCO2. This is a project that's led by my master's student, Liz Farquhar, who's a couple years into her master's now and has really taken this thing from concept all the way to actual field deployments. The exciting advance of this is that there are other Delta PCO2 and PCO2 instruments out there, but they typically cost a couple $1,000s. So at the core of our instrument, we have a very low cost $100 non-dispersive infrared gas analyzer, a $100 sensor called the K30. And we're comparing that to, we have one of the industry standard sensors as well, called the Lycor 840, which the sensor itself costs about $5,000 to $6,000 prior to the crazy inflation of the last couple of years, at least. And those are integrated into instruments that are often in the tens to maybe even approaching $100,000 range when they're deployed on buoys. When we add up everything that we have in our entire instrument package, we're coming in a little bit under 2K right now. And this graph on the right here shows the comparison between the K30 based instrument that we've been building, that Liz has been leading the development of, against the Lycor. And what we've learned is that the K30 isn't quite as accurate. This is something that we suspected based off of some other prior research, other atmospheric examples. This sensor, by the way, was originally developed for air quality, indoor air quality studies, and it wasn't intended for scientific applications. But what's really nice, this third bullet point here, the delta measurement, by subtracting the air side from the water side, we're canceling any drift or any inaccuracy that might occur on any of those in terms of the offset. And so we're not too worried about the overall accuracy, as long as there isn't a significant slope to that inaccuracy, as long as it's not a large percentage, or as long as we're able to characterize it well, we believe that we can get a really robust delta. And we've already seen this in our initial field deployments. We are excited to start deploying it in some seagrass beds and looking at delta PCO2 versus seagrass density. This is where I want to come back to the blue carbon topic that was in the title, which I have to admit I provided back in January of this year. And then it was a few months, obviously, before I actually got here to give this talk to you. And so I wanted to really try to come back. This was the subject that I've been most excited about in the last couple of months, and where I think we can go with blue carbon, marine carbon dioxide removal, and really trying to understand what's happening at a higher spatial resolution through the deployment of many of these instruments, or by integrating these into some mobile platforms as well. And then the very last thing that I want to touch on is that just in the last couple of months, I got involved in the Seahawk and Hawkeye Ocean Color CubeSat project. This is a relatively low-cost satellite that has ocean color measurements that match the specs of CWIPS and NASA MODIS, and we're doing it at 120 meters of spatial resolution. We have better spectral quality for ocean measurements than Landsat and Sentinel-2. Not quite the resolution, the spatial resolution that they have, but we are ideally suited for coastal measurements. This is a project that John Morrison, a former investigator here at UNCW, now retired, and Sarah Rivero-Calle, who is a professor down at the University of Georgia. We're all working together on this along with NASA and some other groups. We're also working through this project on some low-cost bio-optical sensors for both citizen science and research-based validation of these products. And those are projects that are led by brand new master's students, Jesse and Mitch, as well as collaborations with some other faculty. So to try to pull this all together, my three main goals, at least recently, have been monitoring, and especially the topic of water quality. Inorganic carbon has been kind of at the core of all of this, and trying to do so at higher spatiotemporal resolution, trying to really fill in the gaps between the other measurements that we have out there. I'm trying to enable these greater spatial coverage, these better maps, especially through integrating devices into mobile platforms, as well as low-cost technologies. I know we absolutely have a need for the high-cost, expensive stuff, but I think that there are a lot of gaps that we can fill using lower-cost technologies. I also think that providing lower-cost technologies to broader community groups provide some opportunities for other folks to study the questions that they're interested in, and not just the academics from the ivory tower showing up to study what we're interested in. And then, of course, all of this is tied together through the development aspect. I've been working in the kind of maker movement, the IoT ecosystem, to try to work towards simpler, less expensive, and better technologies. This also, by the way, has some really great student training opportunities because it's not super expensive stuff, and there's so much out there on the web that students can use to get started on this. A lot of folks that come to my group have already been working on these sorts of things in high school makerspaces, college makerspaces, and even in their own hobbyist projects. And so all of this hobbyist technology is now at the level where we can use it for real science. So thanks again very much for the invitation, for putting up with the Zoom presentation. I know we're all getting kind of over the Zoom stuff, but I really appreciate the opportunity to join you here. And thanks again for your flexibility and timing.
Thank you very much, Phil. We have time for questions from, maybe we'll start with the live audience first, and then we can move on to the online folks. Hold on, I need to get the mic. So we have one question from Marine.
Can you hear me okay?
Hold on a sec, the question is coming soon.
And also walk.
You could walk to the computer if you want, yeah. Stuff like
I thought
that.
you were telling me to walk. I was like, that's gonna be a little too long.
I was just wondering if, oh. Can you hear me okay?
I can, yes.
Okay,
We're just fixing the other speaker here.
okay, I was just wondering if the smart fin sensors have to be recalibrated once they're actually sent to a user. I know you mentioned the temperature sensor has to be calibrated, but is that just a one-time thing, or is that even an issue in terms of drift or needing to calibrate it in the future?
Thanks for the question. So far, we've seen that they're really stable sensors. We're buying some of the better available low-cost integrated circuits for temperature measurement. And so far, we've seen that they're really stable. So we've done, I wouldn't say a recalibration, but a revalidation after we received them from people who have had them for a few months. We'll need to continue studying that, of course, as we get more of these devices out there and as we have them for longer time periods. But what we've seen so far is that over a period of between 3 to 6 months, the calibration remains really stable, and we can continue to claim that plus or minus 0.05. We're trying to give ourselves a little wiggle room in that, by the way. Most of them are closer to plus or minus 0.01, 0.02, but we say 0.05 so that, you know, if one's a little bit worse, we're still within our range there.
Great. Another question from Dustin.
I was wondering about the smart fin and the. Okay, I was wondering about like the smart fin and how you're going to test the water quality, what you're going to be looking for in the water quality with that.
I think I got about 80% of that. So if you can translate anything I missed, Max, for me. The question was, how are we going to integrate the water quality sensors?
Yeah, I guess the question is, yeah, what kind of other parameters may you be able to integrate, right?
And what they're going to look for.
Yeah, what are you going to look for? What other parameters or?
Yeah, thanks. I did say I was going to come back to that, and I really kind of just basically glossed over the water quality stuff in my last part of the satellite project. So a lot of the satellite validation work that we're doing, the low-cost biooptics, those I see as sensors that we can relatively seamlessly integrate into a platform like SmartFin. And the reason is because everything can be encapsulated behind clear epoxies. And so these biooptics, which have basically an LED photodiode and filters and lenses, things like that, all of that can stay behind the epoxy layer on the SmartFin. Once we start putting things on the actual surface and exposing components to the water itself, you know, a pH sensor that actually has to be wetted, or a dissolved oxygen sensor or something like that, we definitely believe that we can do that, but it becomes a little less viable in the citizen science context because folks are going to be throwing their boards into trunks and truck beds and on the sand and things like that. And it'll just be a lot tougher to protect the sensor as well. But we believe that bio-optics will be the next frontier. I think optical backscattering will be a really big one next, and then chlorophyll fluorescence. One of the other things that I'm going to almost definitely offend somebody in this next part of the answer here, but one of the other things that works to our advantage there is that there's still so much, I guess, variance in the measurements that we're making in a lot of bio-optics. We still need a lot of work to refine what we mean when we say a chlorophyll fluorometer provides a reading of X relative fluorescence units, or we have a reading of some number of nephelometric turbidity units, and figure out what those mean in terms of the biological or the true suspended sediment concentrations. And so I think that we can contribute to that without getting ourselves into too much trouble for overstating accuracy.
Great.
Thank you.
Thank you.
Now a question coming up.
Okay. Hi, great talk. I was wondering, jumping off of the surf fin, I was wondering about the citizen science portion of it. Do the surfers upload this data to, is there a shared app, or do they have access to this data that you're collecting? And what's the interaction between that aspect of your surf fin?
Yeah, absolutely. Thanks for asking that. That's definitely an important part. The user interaction, the user experience, and all of this, that matters a lot to us, both to capture their interest and make sure they're coming back to it. We also want to provide some educational resources through that. So the nice thing about our latest version is that it has the cell modem built in, and so it knows. It also has the wet dry sensor, so it knows as soon as the surfer has exited the water and they've been out of the water it waits for a threshold of 2 minutes out of the water. And then it starts looking for a cell tower and it sends all the data back. So usually by the time someone is off of the beach, the data are already in the cloud. So the next part of your question, yes, it's all totally freely available. And it's through this Axiom database that I mentioned, but that's a more science focused and scientist facing portal. So most surfers aren't necessarily going to go to this place to find their data. And so we are working on an app that would provide some more, think of if you're familiar with something like Strava or Garmin type interfaces, where folks can zoom in and out of maps and have a community that they're comparing stats to, things like that. And again, we really want to provide a lot of the educational and ocean literacy content in those places as well.
Thank you.
Thank you.
Another question coming up.
Hi, it's me again. I was just wondering how to get involved because I actually grew up surfing right off the Scripps Pier.
Nice.
And so this kind of combines my passion. So I was just wondering how I can do something with this.
Well, thanks very much for your interest. I would say if you see my email address on the upper right-hand corner here, hopefully I'm not blocking it with the Zoom features, but if you want to shoot me an email, we're always looking for different sorts of help. And depending on your background expertise, could be anything from data analysis to figuring out better methods for fabrication of the devices, working on the next generation of sensors. One of the really exciting advances I mentioned just briefly is trying to use the motion sensor data to extract wave information. We don't believe that will be necessarily scientific quality wave data because of the surfer's momentum or surfer's inertia that's contributing to the motion of the board. But we do believe that it could be a really valuable metric. And again, we're not making these measurements otherwise in most coastal areas. So I think there are a couple of different areas there, but I'd be happy to chat with you, and thanks for your interest.
Okay. Let's see. No one online. I do have a question for you, Phil, actually, that relates to the CFOX and the supply chain issues. And first of all, the work you've done with the in-situ calibration with the trace buffer in artificial seawater is really neat and super impressive. But I heard that there is some, important supply chain issues with the chips on the Durafet right now. And I was wondering, what's your take on this? And could we do something about this like by making those chips maybe more open source, or that we could build ourselves rather than relying on a company to do that?
Yeah, I think there are a lot of exciting opportunities in the lower cost, more open source, things like that. The chip itself, the Honeywell DuraFit chip, that's a chip that they have all sorts of patents on and would be extremely difficult without some massive fabrication facility, the likes of which, Honeywell and a few other companies are able to make. And so I don't know if that would be easily replaceable, but what I do think is kind of the next frontier for a lot of this is taking some of the other versions of other ISFETs, other glass electrodes, other just technologies in general, and using some of the self-calibrating work. If you have a slightly less accurate sensor, but you have a really accurate calibrant tied onto that, then you could still have a certain degree of faith in that. I've also been working with Sunburst Sensors up in Montana. They build the SAMI pH line of instruments. They have recently commercialized what they call the Fighter instrument. It's a low-cost, discrete pH measurement tool, and it fits in the palm of your hand, and it comes with a little plastic syringe. You take a little sample of seawater, you drop in a little dye, shake it up, and then all of the measurements are done internally, sent to a Bluetooth app, and then up to the cloud if you so desire. And it's about, I think it's maybe $300, $500-ish. I don't want to speak for them, but that's a really exciting opportunity as well, both for folks who want to get involved in making regular measurements using that, or if there are other technologies out there that might not be quite as accurate, but can do continuous measurements, you could go out and you could validate or recalibrate using this lower cost, but still highly accurate spectrophotometric technique.
Right. All right. I don't think we have.
Max, there are 2 people with questions raising their hands on.
Oh, I didn't see that. Sorry about that. All right. So we have a question from Anna, who's online. So you can unmute yourself and turn on your video if you want, Anna.
Hello. That was a great talk. I was actually just in, oh, can you hear me?
Yes.
Okay, cool. I just heard me playing back to myself. Okay. I was actually just in Maui with Yui, and we were deploying beams, which I don't really remember the whole acronym, but I know pH is a part of that. And my current project is actually working on trying to understand various aspects of coral crevice ecology and like all the tunnels and stuff. Wow. So it'd be really cool if we could understand pH in there. And he, of course, got, excited about talking about various ways, but I was wondering if you had any thoughts on, I mean, this Fighter instrument sounds really cool, if that's what it was called,
Right.
For discrete measurements, but we would also be interested in diurnal stuff, potentially. But if you have heard of anyone using the CFOX and like, I don't know, modifying it in some way to kind of make it longer and less, like more easily fit into somewhere that's small and deep. For a crevice idea, but I don't know if that comes to mind, anything that you've seen anyone else do, but very specific question, I realized.
Sure. Yeah, thanks for the question. I figured there had to be folks in the audience who had either worked with Yui or at least knew him well from his prolific experience with all of these things and proximity.
Totally.
Yeah, so that sort of touches on what Max was asking too with the supply chain issues. The rate limiting step for you there is going to be just getting your hands on an extra DuraFit right now. Okay. But there are alternative sensor technologies out there. We did a little bit of work with someone from sorry, I'm blanking on exactly. They were at one of the CSUs in Cal Poly. They were at Cal Poly and came down to work with us for a little bit, working on evaluating a couple different pH sensor technologies, and made it pretty far in figuring out that there are other ISFETs that might come close to replacing a DuraFit. I think there's a whole lot of work before you could actually make a claim that it works as well as a DuraFit, because now over a decade's worth of work has gone into that one particular chip. But there are alternatives, and I'm really interested in working with folks who would be interested in exploring those. I know the Mbari team is as well because of that rate limitation. So a lot of folks are exploring alternatives, but yes, I think there are a lot of opportunities there. And all you're really talking about is a longer cable. And then, of course, deployment length is going to be, and biofouling will be limitations, but making a longer cable is never that big of a challenge.
Okay, cool. Thank you so much.
And finally, we have a question from Jessica, and you can unmute yourself and turn on your video if you want, Jess.
Hi, can you hear me?
Yes.
Awesome. Thanks for the great talk. So I had two questions in a way. The first one was it's both about the SmartFin technology. So right now with the SmartFin technology, do you see it kind of limited geographically in terms of use, where it's predominantly used maybe in Western countries like the US, Europe, Australia? And if so, like what would be the next steps to expand it to places where we don't have as much regular sensing going on, such as like Africa, the Indian Ocean, etc.?
Thanks for the question. Yeah, that we're even more severely limited right now than you implied. We're not just Western countries, we're predominantly in the San Diego region so far. That's where most of the early fins were deployed. And what was exciting about that deployment is that in the paper that I showed that we published recently, we did a comparison of all of the smart fins that had been surfed in sort of this informal ad hoc network around the Scripps Pier. We compared those to the Scripps Pier thermometers, and we saw a really good agreement, which might not sound surprising. It might not even really sound all that interesting, but because we have the Scripps Pier measurements. But if you take it to a place where you don't have long-term time series, you don't have peer deployments, you don't have these assets, then to your question, yes, I think that there's a lot of opportunity there. I think there are a lot of community groups that would be really interested in this. We've gotten some interest from folks that want to do monitoring near like power stations and the effluent and the changes in temperature that they see there, or near other wastewater disposal areas. You know, of course, we don't have the exact water quality instruments to do that precisely yet, but you could look at some proxies. And I think that something like this could scale pretty well for that. Again, we're looking for areas that might have some sort of cellular access, but we're also looking into some alternatives like a Bluetooth app to download the data, or even if it's just a hardwired download to the computer itself, something like that. But in short, yes, I think there are a lot of opportunities there, and hopefully we can contribute.
Awesome. That's really interesting to know where it's been located so far. And then the second part of my question was, do you think the SmartFin technology could be adapted into like a chip that divers could carry, like, which obviously gets into issues with pressure and things, but a lot of divers dive right near the reefs, and you could getting the temporal scale of pH right near corals and other like gradients.
Yes, absolutely. A lot of folks have expressed some interest in something like that. I've seen a couple citizen science dive programs that are out there, and folks will upload their dive computer data to a common repository and provide these temperature profiles, of course, with the pressure sensor that's already integrated into the dive computer.
Yeah.
And they've learned some pretty cool things. I know someone, I think down in Florida, is looking at that now. She did her PhD out in Australia and looked at similar things. I haven't seen anyone doing it with pH integrated onto that, but I definitely think there are opportunities there. And then dive computers aren't really calibrated to the same standards that we use for temperature. So if you could further improve the temperature calibration on that, I think you could get even further. And then, yeah, I would love to, I've reached out to some of the dive computer companies and asked if there'd be collaborations there. I would love to get into that. I think there's definitely a lot of opportunity there.
Very cool. Thank you.
Thank you.
Great. I think we're good. Well, thank you very much, Phil. Once again, it was a wonderful talk. Thanks for the time.
Thank you.
And everyone, this is it. Bye-bye. Thank you.